Welcome to week 11 of computational quantum chemistry, and this week we are going to discuss about solvation models. Up to now, whatever calculations we have done is in the gas phase. We have considered the presence of environment by doing QMM calculation, but we have never talked of solvation as such. So this week we are going to talk of solvation. Now, the solvation can affect the chemical reaction in multiple ways, and remember, most of the real life processes actually happens in a solvent. A number of gas phase reactions are pretty limited, and in biology almost everything happens in the solution phase. So, many reaction takes place in solution. There can be two range of effect which you can separate them out. One is short range effect, typically concentrated in the first solvation sphere. Example, hydrogen bond, potential orientation near an ion, some charge transfer kind of interactions. They are generally concentrated in the first solvation sphere. So, how you treat the molecules in your first solvation sphere is actually of primary importance. Now, the second thing is long range effect. Among them is polarization. So, basically the presence of the solvent actually polarize the solute, as well as the solute can in turn back polarize the solvents. So, this kind of effects can be pretty long range, and sometime to get many properties right, you need to take care of this long range polarization pretty accurately, especially if you are dealing with excited state or treating a charged molecule. Now, the solvent models which are available for molecular simulation can be briefly categorized into two major categories: explicit versus implicit solvents. So, in explicit solvent, what happens is that you take the solute and place real solvent molecules. Here in this case it is water. So, you place real solvent molecules around the solute, and this the explicit interaction between the solute and the solvent actually gives you the effect of the solvation. Whereas, in the case of implicit solvation, you treat the solvent as a continuous media with some kind of a dielectric constant, and so basically solvent is considered as a dielectric. Of course, one can take care of the explicit interaction by playing some tricks, but mostly the major effect comes from the dielectric effect of the solvent, and for polar solvent that can be the major dominating effect. Now, there may be a third category which actually can give you compromises between the two. We will discuss what is the problem and the advantages of explicit and implicit solvation, but there can be some hybrid kind of an approach which can actually give you a treatment which is actually in between the explicit and the implicit treatment. Now, so in the case of the hybrid treatment, you have explicit solvation for the first solvation sphere, because we have discussed the first solvation sphere is where the most important thing happens, and take the long range affected by treating surrounding solvents by a continuum model. Now, when you try to do mix and match things, it is not always very straightforward, because in principle they look very good, because this hybrid model contains best of both of the world, both the implicit and the explicit solvents, and computation costs are somewhere in between. But often when you do this mix match, it can lead to physical artifacts, so you should be very careful about it. And this, when you do this kind of a treatment, where you do this hybrid kind of a treatment, generally you treat the inner solvation cell using quantum mechanical method and outer solvation cells classically. Now, among the two solvation models, if I want to see the features and the advantages and the disadvantages, so in the case of explicit solvation models, all the solvent molecules are explicitly represented. So, thing is that you can mimic all the interaction explicitly, so detailed information is provided, these are more accurate. Disadvantage is this: expensive for computation, because remember, first of all I have to take care of all the solvents explicitly. Okay, you may say that, okay, why I need to take all the solvents explicitly? Because the interaction actually come from the effect of the solvation. Now, you can further argue that, okay, I do not need all the solvents to be taken in the expensive QM region, I can take them as a molecular mechanics region. Anyway, my first solvation cell is what is important, but still you need to do calculations which are multiple of them, because you do not know what is the actual solvent distribution around the solute. and that is a dynamic property, the distribution will change. So, what you experimentally observe will be an average of all the snapshots, all the solvent distribution configurations. Now, to model that, that means you need to do calculations on multiple of solvent distribution and then do some kind of an averaging of it. That can be very expensive. In the continuum solvation model, it represents the solvent as a continuum media. It is very simple, inexpensive to calculate, it generally has very little additional cost over a single point calculation, but problem is that it ignores the specific short range effects. If you are dealing with a system where hydrogen bondings are very important, or there is a charge transfer between solute to solvent or solvent to solute, in that kind of state this continuum solvation models generally completely fails. So, you need to pick and choose depending upon what kind of problems you are dealing, what kind of accuracies you are looking at. So, we will come into more details about the more details of the theory, so you can make a better informed choice. Now, what happens in the continuum solvation model, that you consider the solvent as a uniform polarizable media of fixed dielectric constant epsilon and having a solute molecule placed in a suitable shaped cavity. Of course, formation of cavity actually destabilize the system, but that get compensated with the effect of the interaction of the solute with the solvent. So, the solute induces polarization at the interface of the cavity. This polarization acts back on the solute, changing its wave function, and various solvation models different scheme for the evolution of this solvation effect. So, this is how it will go like. So, first the solute polarizes the boundary, and the polarization in the boundary so that will induce charges and dipoles here, and that will in turn change the wave function of the solute, and various solvent model uses different scheme for evolution of this, how this induced dipole moments and charges are produced, how they are coupled with the solute. So, depending upon that different solvation effects happen, and problem arises when electrostatic do not dominate the solvent solute interaction. So, the basic approximation between continuum solvation model is that the electrostatic interaction between the solute and the solvent is a dominant factor. There are cases where there can be other interaction, there can be dispersion, there can be hydrogen bonding, there can be charge transfer. Although it is an electrostatic, this cannot be modeled properly because there is no solvent structure present in this kind of implicit solvation cells. When talking about implicit solvation models, you will hear various terms like CPCM, COSMO, SMD, various kind of solvation models you will see. Actually, all the solvation models, implicit solvations, work on a very similar principle, although some people claim that their solvation models are better than the other, but generally the working principles are very similar. So, they differ mostly in 5 aspects. So, how the shape of the solute cavity and what is the size, method of calculating the cavity creation and dispersion contribution, how the charge distribution of solute M is represented, whether the solute M is described classically or quantum mechanically, and how the dielectric medium is described. Depending upon these 5 things, we are going to get different kind of solvation model which has different names, but the actual working principle is very similar. Now, solute cavity size and shape, if you think of, if you use a bond model, it will use a spherical cavity. If you are using Onsager model, ellipsoidal cavity, and if you are using the modern implicit solvation model like CPCM or COSMO, so then in that case it will use the cavity which is made of the van der Waals radii of the atoms constituting the molecules, and this is the radii. Actually, you can see the radial distance r here. Now, the cavity, as we discussed, that for the simple model the cavity can be sphere and ellipsoid, and for the molecular shape models, the more modern models CPCM, COSMO, they use the van der Waals surfaces. So, the way you do the van der Waals surfaces, that you actually put a sphere around the atom where the sphere actually has a radius with the van der Waals radii of the particular atom. So, this is for oxygen, this is for hydrogen, this was, and how the density distribution along this one is described is generally obtained by quantum mechanical wave function or electron density. Now, so you will hear these 3 terms: van der Waals surface, solvent accessible surface, and solvent excluded surface. So, these terms, just to make it clear, the van der Waals surface is a surface which is constituted by the van der Waals radii of the particular atom. Now, if I do this one, that essentially means that the space in between this radii, like this place here, this cannot be accessible to the solvent. So, these are called solvent excluded surface. Whereas, if I take a sphere of a particular radii and roll over the van der Waals sphere, I will get also a surface. So, I am taking a sphere of a particular radius, the radius depends upon what kind of solvation models you are using, but if you take this sphere and you roll it on the van der Waals surface, and if you draw a line passing through the middle of the sphere, the surface you get is called a solvent accessible surface or SAS. So, these are the kind of surfaces you need to describe for the solvation models. Now, the most famous of the solvation model, the conductor-like polarizable continuum model or CPCM. The conductor-like polarizable continuum model is an implementation of the conductor-like apparent surface charge method. In this model, the solute is placed in a cavity of roughly molecular shape described by the van der Waals radius. The solvent reaction field is described by the apparent polarization charges on the cavity surface, which are in terms determined by the solute. These changes can be treated as punctual or point charges or can be modeled using spherical Gaussians. The cavity in the ORCA is constructed differently depending upon how the charges are treated. So, both the point charge model and spherical Gaussian models are actually available in ORCA. In the case of point charges, the cavity is generated through G-pole algorithm either as a solvent excluding surface or solvent accessible surface. We have described what they are. When Gaussian charges are considered, the user can choose between a scaled van der Waals surface or the G-pole solvent excluded surface, and the charge positions are determined following a Lebedev quadrature approach. This scheme is known as Gaussian charge scheme. This scheme generally gives you continuous potential energy surface. So, if you use the standard point charge model, sometimes you get discontinuity when you draw potential energies. Now, the question is that what changes for the QM model. So, we have came to know what actually we do for the solvent, how we treat it, but what about the QM method. So, until now we have not said anything about how the solute charge distribution is treated and how it can be affected in the presence of PCM. PCM has been developed so as to couple a continuum description of the solvent with a quantum mechanical description of the solute. This coupling is based on the definition of an effective Hamiltonian in which the vacuum Hamiltonian is 0. So, whatever Hamiltonian we have treated up to now in the gas phase that we consider as a vacuum Hamiltonian is 0 is supplemented with a new term representing the electrostatic interaction between the solute and the solvent. So, now I get an effective Hamiltonian which contains my gas phase Hamiltonian plus an extra potential comes due to the electrostatic interaction between the solute and the solvent. So, the SCF procedure leads to the variational minimization of the free energy of the solute. So, when we were discussing the gas phase Hartree-Fock calculation, what we are minimizing was the electronic energy. So, here we are calling it free energy, although if you see the first term it is nothing but an electronic energy, but you also have a term which describes the solvation free energy. So, the total thing I am calling free energy, and instead of minimizing the only this term, I am minimizing the full G. Using the conductor-like boundary condition, the electrostatic potential can be determined by this expression, and where V and VQI is the electrostatic potential due to the solute and to the polarization charges, and R is the point on the cavity surface, and NQ is the total number of solvation charges, and the vector polarization charges can be determined by this. So, these are the theory. If you are interested in, there are detailed review available where you can read the theory. But from a user point of view, the ORCA input file only needs certain parameter to take care of the solvation effect, and after that it is completely black box. So, these are the full set of parameters which you need to do the CPCM. Do not get scared, generally it is enough for most of the cases to give the additional keyword CPCM water. If you use the CPCM water, that is the only thing you need to take care of taking care of the solvation effect, and these are the available solvents available in ORCA. If you want to change it to other solvent, generally it is sufficient to give the epsilon and the refractive index value, which you can find out from the some reference in the literature, and then you can do the calculation. So, for most of the cases you do not need to specify these values, and generally it is not a good idea to actually tinker with these values. Most of the cases the default values are good enough. And as you remember, ORCA supports two kinds of solvation charge scheme, the point charge scheme and the Gaussian charge distribution scheme, depending upon what kind of things you are doing. For most of the cases, point charge scheme is good enough. If you are interested in potential energy curves and you are getting discontinuous values with the point charge scheme, then you should switch to Gaussian charge scheme. Now, one of the first example we will see on the effect of the formaldehyde is to calculate the IR frequency shift of formaldehyde from gas phase to water using B3LIP DEF2 TZVPP method. We have tried this problem before, and we can try to see how the solvation effects actually changes in the case of formaldehyde. So, let us go to Excel, because first of all the things what I need is the bond length and bond angle. First let us get the bond parameter. CO, CH and HCH angle. Let us start with the gas phase calculation. Most of the cases it is a good idea to, if you want to optimize in the presence of solvent, it is really a good idea to first do the optimization in gas phase and then put the effect of the solvents. So, let us draw formaldehyde. Make it oxygen, adjust the hydrogen, this one double. First let us optimize for the gas phase. Freak B3LIP DEF2 TZVPP Rij cos x. So, let us make a new folder here, week 11. The formaldehyde gas. Let me increase the view a little bit. There is some input file problem. let's see what is wrong. Ah, I forgot to write def 2 TZVP, which is all right.